Hi everyone, and welcome to the last unit in chemistry this year. We're going to start this unit with a topic called thermodynamics. Thermodynamics is the study of energy in chemistry and chemical reactions. We're going to start off with a couple of definitions. The first is temperature. We've talked about temperature already. It's the average kinetic energy. It has to do with the motion of the molecules, and we spent a lot of time on that when we talked about gas laws. Temperature is measured in degrees Celsius or Kelvin. A completely different type of energy that you do not want to confuse with temperature is heat. Okay? Heat energy is the energy that is stored and released, either in chemical bonds, through other means. It's a way of losing energy from friction is often lost as heat. So it's kind of lost energy. But of course, if one thing loses energy, something else can take it in. So it's also an energy that can be used in some reactions. When we store energy, so we call it sort of lost or stored energy. This energy is measured in calories or joules. Calories, which uses the abbreviation CAL, that's the amount of energy it takes to make 1 gram of water change by 1 degree Celsius. The other unit that we use sometimes is joules, which has the abbreviation J. Okay. The thing about calories, we're all familiar with calories from dieting and food and nutrition. When they say calories, they actually mean kilocalories or 1,000 calories. A calorie in chemistry is actually a much smaller amount of energy than a calorie when you're dieting. That's kind of important to know. Okay, there is heat energy that is lost or gained in a chemical reaction we refer to as enthalpy. We sometimes call enthalpy the heat of reaction. And just like any other heat, it's going to be measured in calories or joules. The symbol we use for enthalpy is delta H. Okay? There's one other term that I want you to be familiar with, and that is the specific heat capacity. Specific heat capacity uses the symbol Cp. It's the capacity at constant pressure. Don't worry about the constant pressure part so much. You just need to recognize that symbol Cp. Specific heat capacity is the amount of energy that it takes to raise 1 gram of a substance by 1 degree Celsius. This isn't just true for water like a calorie. It's true for anything. This is really important to know the difference between heat capacity and a calorie. Calories are just for water, and it's the definition of a temperature unit. The specific heat capacity of water happens to be 1 calorie. But this is actually the reason, we've talked about this a little bit before, why the ocean right now, the water is very cold, even though the air is warm, because the air has a very, very low heat capacity. And so the sun comes out, the air warms up. The sun goes down, the air cools down. Water, it takes a lot more energy to change the temperature. So the sun has to be up for a long time to give it enough energy to raise its temperature. But on the other hand, the sun has to be away for a long time for it to cool down also. So now that we know these terms, I want to talk a little bit about what happens when you heat something up. Our favorite substance is water because we know a lot about it. So this is a form of a diagram. It's an energy diagram. This is what happens when you start off at a low temperature and you increase the energy. So I'm going to start at a really low temperature. And I'm going to add energy. And it kind of makes sense as you add in energy, things get to a higher temperature, right? Add energy, the molecules move around more. But at some point, that temperature is going to stop getting higher. It's actually going to flatline for a little bit. We call that temperature the melting point, or the freezing point if we're going in the other direction. So it's kind of important to notice that at the melting point of something, if this is water, this is 0 degrees Celsius, okay? Below the melting point, we have solid, ice if it's water. And that solid is getting to a higher and higher temperature. Then it gets to its melting point, and the entire time it's melting, the temperature doesn't change. The same thing is true for freezing. If I'm going in the other direction, I'm starting off hot and cooling it off, the temperature doesn't change until all of it is frozen. Okay? Then eventually, we have our whole thing melted, and we change temperature again. Okay, liquids can take a little longer to heat up. It doesn't have to be the same slope for the solid as it is over here for the liquid. But here the liquid is heating up, heating up, heating up, until we reach the boiling point, which for water is 100 degrees Celsius. And we flatline again. So when the phase is changing, the temperature isn't. Right? And that constant temperature is the melting point or the boiling point of the substance. And then once it's all gas, the temperature can get raised again. Gases tend to heat up very quickly, so they tend to be a much steeper line. Right. We can actually calculate how much energy we have to add to make certain things happen. So let's say I wanted to heat up liquid water from about 5 degrees Celsius to about, I don't know, let's say 10 degrees Celsius. Okay. How much energy do I have to put in to do that? Well, in order to calculate that, since I'm staying in one phase and changing the temperature, I'm going to use a heat equation. And this one, Q equals mCp delta T. Q is heat, energy. Okay. M is mass or moles, depending on what we're talking about. You have to look at the units of your heat capacity. Cp, that's the heat capacity. And delta T, you've seen this before, is a change in temperature. Now this is kind of important. Delta T could be positive or negative, which means Q can be positive or negative. Go on to my page for a second. So if Q is positive, that means that energy is going into the system. If Q is negative, energy is going out. So in chemistry, the sign tells you what direction the energy is moving in. So in the case of our water, if I have, let's call it 38 grams of water. Actually, let's go 36 grams of water. Sorry, 36 grams of water heated from 5 degrees Celsius to 10 degrees Celsius. And in order to do this, I need to know the specific heat capacity of water, which is 4.18 joule per mole Kelvin. Now we already know that 1 degree Kelvin takes up the same difference as 1 degree Celsius, so we do not have to change the temperature over to Kelvin here. But we do need to change our grams into moles. I'm just going to do this with quick rounded numbers. Okay, so I know there's about 18 grams in 1 mole of water, so 36 grams. That works out to 2 moles of water. Okay, so I plug it into my heat equation. Q equals mCp delta T. Heat is equal to the moles in this case. 2 moles times my heat capacity, 4.18 joule per mole Kelvin, times my temperature change. Temperature change is final minus initial. That makes sense. I'm going to get a positive number because I have to put heat in order to get the temperature change that I'm looking for. So if I do this, this is 2 times 4.18 times 5, and that equals 41.8 joules. And that's how you calculate how much energy you need to add to heat up water. But what if I wanted to figure out how much energy I need to boil a certain amount of water? Okay? How much energy does it take to completely boil water? So let's again use nice easy numbers. So let's say we want to use about 10 grams of water. Okay? In this case, the temperature doesn't change. So we can't use this equation. So let's kind of extend this a little bit. If the phase changes, no temperature change is going to happen. So we have a slightly different equation. In this one, we have Q is equal to, again, mass or moles, times the heat of fusion. Heat of fusion is the energy it takes to melt water or anything else. Okay, so fusion and freezing or melting are the same thing. Okay. If we wanted to do boiling, we would use heat of vaporization. Delta H, vape. Now, since I looked up the heat of fusion before I started this lecture, we're going to actually do a heat of fusion pump. We're going to freeze water. How much energy is needed to freeze 10 grams of water? Okay. In order to do this, I need to know that the heat of fusion for water is equal to 333 joules per gram. So I can just plug this into my formula. Okay, the mass is 10 grams. The heat of fusion is 333 joules per gram. So it is going to take me 3,330 joules to melt that water. Okay, take a second, pause if you need to, make sure you understand what we did there. Okay, welcome back, if you paused. We're going to switch gears a little bit. We're going to talk about what goes on with energy in the middle of a reaction. So the first thing that we need to know is there's 2 basic types of reaction. Exothermic and endothermic. In an exothermic reaction, we give off energy. We recognize it because the energy at the end is lower than the energy at the beginning. The energy of the products is less than the energy of the reactants. The delta H is always negative for an exothermic reaction. And as you can imagine, it's a little easier for things to happen if they give off energy than if you have to add energy to them. Right? The other basic type of reaction is an endothermic reaction, which you recognize because the ending has more energy than the beginning. So the H of the products is greater than the heat of the reactants. And in this case, delta H is positive. So that would be how you'd recognize an exothermic reaction or an endothermic reaction. My exothermic reaction is red because they feel hot. They are giving heat to your hand, so you will feel hot. Endothermic reaction is in blue because these are going to feel cold. They're actually taking energy away from your hand to make the reactions happen. So you'll notice I have a couple of lettered lines here. These lettered lines are important for you to be able to recognize. So on both diagrams, A is the heat of the products. That's how much energy is stored in the bonds for all the products that you're... Oh, I'm sorry. A is the reactant. I apologize. Okay. That's how much energy is stored in your reactants. You recognize it because it's the one on the left. It's your starting point. Right? Letter B in both of them is the energy of your products. A nice simple thing to figure out is how much energy the reaction used or took in. So that's letter C on both of them. C is delta H, or the enthalpy, and it is defined as the heat of the products minus the heat of the reactants. So when the products are higher, we have an endothermic reaction, and it's positive, like we said over here. When the products are lower down, like here, the delta H is going to be negative, and it's exothermic. The last labeled line on here is D, which is the activation energy. You might notice on these diagrams that no matter what, we go uphill first. We go uphill and then downhill in all reactions. Okay? You always have to put in a little bit of energy to get going. As much as some of you think I am nothing but energy in the mornings, I do in fact use an alarm clock to wake up. That alarm clock is my activation energy. Okay? Activation energy is that little bit of energy you need to get the reaction started. Obviously, an exothermic reaction only needs a little bit of energy, where an endothermic reaction has a big hill to climb up, so they have large activation energies. So now we're going to add to something you learned in chemistry. You might notice these green dotted lines in here. That is what happens when we add a catalyst. You guys learned in biology that a catalyst is something that speeds up a reaction. That is still true. The addition for chemistry is we're going to tell you how. It speeds up a reaction by lowering the activation energy. When you get into higher levels of chemistry, you'll actually talk about the mechanisms that it uses to do that. But for right now, all you need to know is that it lowers the activation energy, and that allows the reaction to happen faster. So we know that things happen more naturally when they're giving off energy. A reaction that's going to happen all by itself is called spontaneous. All right, so spontaneous means happens by itself. Okay, if you put a rock at the top of the hill, it'll roll down the hill by itself. It's not going to roll back up by itself. Right? There's another factor though. It's not just the energy that determines whether or not something's going to happen. There's also something called entropy. Entropy uses the symbol delta S, right? And entropy measures the randomness or disorder. The more different ways something can be, the higher the entropy. So gases have very high entropy. They can be all over the place. Liquids have a little less. And solids are stuck in place, so they don't have a whole lot of entropy at all. Another way of looking at entropy is messiness. When we go home, we tend to be tired from our day, and so a lot of times we just sort of kick off our shoes and drop our jacket and kind of leave them where they are, because that's the easy thing to do. Right? That's a high entropy state. Things aren't where they belong. But eventually, we do put our shoes away and we do hang up our jacket. That is a lower entropy state. Okay, so what does entropy have to do with being spontaneous? Well, spontaneous is the easy to do thing. So if we're messy, we're going towards gases, we have a lot of randomness and chaos, the reaction is going to happen much better. At the same time, giving off energy is going to work a lot better. So these two things are in competition with each other. So in order to figure out if a reaction is actually going to happen, we use something called the Gibbs energy. The Gibbs energy is the enthalpy minus the temperature times the entropy. Okay? You don't really have to know a whole lot about this. You just need to know that if delta G is negative, it's spontaneous. If delta G is positive, it's not spontaneous. And honor students, you should know that when delta G is 0, it's at equilibrium, which we're going to talk about next class. Okay? But what you do need to know, everybody, is how to tell if delta G is going to be positive or negative. Because usually we tell you about delta H and delta S. Enthalpy, delta H enthalpy, and delta S entropy. So we said giving off energy exothermic makes it spontaneous. Being more random makes it spontaneous. So if delta H is negative and delta S is positive, the reaction will be spontaneous. Every time. By the same token, if delta H is positive, it's an endothermic reaction, and it's more ordered, then it's not going to happen without help. So we call that not spontaneous. Does that mean it won't happen? Of course not. We know that water becomes ice. We can take away energy and go from liquid to solid, so become more ordered, and it does happen. But we have to do something to make it happen. But what about the gray area? When we did the stuff on the periodic table, that sort of off-diagonal stuff, we said don't worry about it. Here you need to know. So when the enthalpy, delta H, and the entropy, delta S, are fighting with each other, the thing that determines who wins is temperature. If the temperature is high, delta S wins the fight. So we know that we want delta S to be positive for a spontaneous reaction. So if both delta H and delta S are positive, so delta S is spontaneous but delta H is not spontaneous, high temperature is going to make delta S win. So when both things are positive, it is spontaneous at high temperature only. If the temperature is low, then it's not going to happen without help. Okay? when we have delta H and delta S both negative, right? We can't make both things negative. Right? Delta S and delta H both negative. Right? Again, temperature makes the difference. So here, the delta H makes it a spontaneous reaction. The delta S makes it not spontaneous. So if we want it to be spontaneous, we don't want delta S to win. To make sure delta S loses, we make the temperature low. So if both things are negative, it only happens at a low temperature. So here's the good thing. Most of us think of negative as low and positive as high. So when both things are positive, it works at high temperature. High for positives. When both things are negative, it's low. Hope you enjoyed this lesson on energy, and I will see you in class tomorrow.